automata, CNTFT, TFET, VLSI, digital microfluidic biochip, computer architecture and hardware. Currently, his research focus is on quantum computing, adiabatic quantum computing, quantum communication and cryptography. Now I request Dr. Kunal sir to take over the session. Thank you. Over to you, sir.
Thank you, sir, for my introduction. Actually, I'm very delighted, and when Professor Vijay More invite me, and I come to know they are organizing the FDP on quantum computing, and I whenever in a world is quantum computing FDP or any such type of things are going on. So I am actually a part of that. Try to be. So I want to contribute in that quantum computing world. What I have earned in last 10 years. Okay, uh, 10 to 15 years actually. Mm, Professor Panigra is also my one of my research collaborator. Very recently, my student published a paper with him, and I want to express that to all participants. This is a very innovative and upcoming field of research, and not only research, it is a reality now. Industry also taking that very seriously. Can you see my screen? By the way, I am COVID infected. Though we are in a virtual mode, I will not infect you. Uh,
Yes, sir.
but my voice might be lower. Uh, so for that, I am taking sorry for that. Uh, Sometime it may be appears a cold and cough.
So before the session, I wanted to say that I am very much thankful to you. Besides your COVID infection, you have agreed to continue our session. So thank you, sir.
Sir, it's our duty that your young generations and new generations, those are interested for quantum computer,
Hmm.
we should bring them together.
Yes, sir.
That's why I am here,
Hmm.
and I will be always for here in any opportunity I come to know. Uh, it's my pleasure actually. Maybe my cold and cough and COVID is not affect badly this time. So this is today's my lecture anyway. I should start because it will take a lot of time because all participants will also need to do some hands-on. As I told to install Python and your dweb portion to install. I will consider two things as much as I can. One is a one D wave, that is quantum adiabatic computing, and IBM Q. You can see the dark star. Dark star is my one of the US company which actually associate with us. They have given a consultancy project to me to solve on their behalf. So these dark stars. So here I am actually research consultant. I have a recruited a few intern and research associate in that team from that project, and we are dealing with mainly with D-Wave actually. Uh, is a wave which is actually now commercially using in USA and Canada. So now, uh, first, can you see my screen?
Yes, sir. Your screen is visible, sir.
Yeah, yeah. Now the second slide is showing
Yes.
different kind of quantum computers.
Yes, sir.
So
Different kind of quantum computer.
okay, okay, that's okay. So what you can see, there's a different list of quantum computers that are being developed in our current era. firstly, I must say that D-Wave from Canada is developed in a era of around 2016 onwards, 15, 16, that's way. And now they are developed 5000 qubit quantum computer is a quantum annular, is a which is quantum adiabatic computing. And whatever the discussion actually going on in today's or in these type of uh, seminars or workshops, that's mainly in a superconducting quantum computers on a gate level quantum computing. These all are considered as a NIQS. Okay, noisy intermediate states of quantum, I'm sorry, NISQ. Okay, uh, NISQ. So IBM, Google, RDG, these all are come to that part. And IBM started in the 2017. Then another important is the ion trap quantum computers come, and then finally in a year of 2019 and 2000, this time the Honeywell comes with the Microsoft, and with the Honeywell they comes with another ion trap quantum computers. And photonic based quantum computer is done by the Zandu, that is a gate level. So you can see that these all are gate levels, and only the D wave working with the quantum annular or adiabatic quantum computers. I'm not going to that which one is the best, which one is the uh, giving the appropriate results, which can be done in the commercially. I am just going to that uses of the quantum annular and usage of quantum uh, NI, NISQ platforms. Basically, as you know, the NISQ by default you can't accelerate your quantum beats. So what you need to do, you need to make your problem into small pieces. As Panikray says that you first develop your Bayesian network for your problem. Suppose you have a big graph and you have a limited number of qubits, so then you go for a part of piece of your problem and you get the result and combine the result, and the old think of discussion, that is divide and conquer, because your number of qubits are limited, while in your real life problem, your in your real life problem you can have your very large amount of data, and then you want to get the entire result, so that this NISQ quantum computer is limited to your number of bits qubits, because it's a noisy interface. So noisy intermediate states, so you cannot accelerate your number of qubits very easily. So it's very difficult. But your quantum annular, which is now currently using in a world as a commercially using, that is D-Wave, and these all are the number is a quantum computer currently available. You can access these quantum computers by Amazon Bracket is a common platform in which you can get all the processors, uh, except you can get the Honeywell. They are not collaborated with that. You can use the Amazon Bracket and pay some money monthly or annually packages, so you can access all those things. But today I will show you that how you can use the D-Wave freely in India. Now is after 2021, India is collaborated with in government of India is collaborated with D-Wave. Now India can use that. But when I started with working with D-Wave, that time it was not Indian. No Indian can have this free access. So So still, what are the problems we have appeared? Definitely, we are interested to solve. First thing that you must understand, not all problem you need not to solve by a quantum computer. So quantum computer should not be replacing the all classical problems. Though those classical problems are solvable by classical computers very well, that you are let them to solve that way. Where you have opportunity to get the better result, then you move there. For example, that is a factorizing a large prime numbers. Whether it is a worthy to solve the factorizing of a large prime numbers, yes, Shore has done this, but Shore has done theoretically. Now still that much of amount of number of qubits in case of gate level quantum computer is not available. Gate level quantum computer means NISQ. So that much number of quantum compute gates qubits are not available right now. So we are now safe because factorizing a large prime number is a basic part of your any cryptographic algorithm, right? RSA algorithm. So is it required? One thing, that is it required to solve it? Maybe your answer is yes. Any mathematical requirements, that type of factorization is required, or cryptanalysis you required this. So very well, then now this the search a very large or huge data that can be done in a linear time. Is it required? Yes, definitely. If you can able to reduce the searching time of a in from order of n to any lesser amount of time, so that will be accepted. So here is the Grover's represents that order of root n. So this much of thing is known to the people, those are actually nurturing with the quantum computer platform or any basic idea about the algorithms. They know about that. So Grovers can do. Now there are still research is going on that whether we can do in a linear time, in a constant time. Okay. So in some specific cases, we can do some constant time searching as well. Okay. So then the problem is the optimization problem. So optimization is definitely you require to solve that. Maybe you know that a simulated aniline you done in the classically in that way you use that to optimizing problem, and can you optimize much more, that will be your expected results. Okay. So like your portfolio for financial purpose you can have, or maybe any other optimization that you are expected to do. Maybe the all such of the problems is those are empty problems, you are interested to solve them by a quantum computer. So now let us these are the basically gate level quantum computer NIQS, and now qubits. This all every speakers has already discussed about the qubits. I'm not going inside that. That qubits is a one quantum particle as more in represented in a Bloch sphere, and this is represented by psi. Psi is the alpha, 0 is the initial state, and 0 and 1. Alpha is a probability of happening, alpha square is a probability of appearing the 0, or beta square is a probability of appearing 1. And this is the superposition of 0 and 1, and value of alpha and beta represent that how percentage of possibilities to be it's 0, and a percentage of possibilities to be 1. Now difference between the classical and quantum, the classical it's beats are like a switch. and it can only be either 0 or be 1, but in a quantum it will be a superposition of 0 and 1. The power of quantum computer is a superposition, entanglement, and quantum interference. This already are discussed by many speakers in this session. But now the quantum annular. In a quantum annular, what we actually planning to do, whatever the my problem is, we will convert the Hamiltonian. We will calculate the Hamiltonian is a mathematically, and Hamiltonian I will go for Hamiltonian with a lower energy state. Which one is a lower energy state? That will be the very stable energy states, and that state will be specified this way. So you can see, I will show you one video. You can see this is a high energy level, and this gradually the low energy level. You have given some magnetic field and some superposition state, and you can get that this type of things. So this showing that this is a 0, this showing that this is a 1, and is a superposition. So it's a 50% superposition of 0, 50% superposition of 1. So both are in a lower state. Now you can see, if you apply some magnetic field, so zero state will be in a higher energy. So zero state moving to the higher energy, but one state is in a lower energy. So this is the high probability to be that is a lower state, and so high probability of this state will be considered as a zero state. Okay. So now you can see that one video. You are applying a magnetic field, and it's becoming 0 and 1, and this is a superposition of 0 and 1 after applying the magnetic field. Though both magnetic field in the opposite direction, right? Now you are applying the positive magnetic field such that is the zero's energy level get high. Now you can see the two bits, and you are giving the superposition, and the 2-bit superpositions, this is a coupled, so either 0 1 or 1 0. So this is the coupler makes the opposite qubit the favorable, right? So the 0 1 and 1 0 are in a lower energy level. It could be that the case that 0 0 and 1 1 is a lower energy level. So in that case, you can say this is nothing else a Bell state you are forming. So this is the showing that the system is get entangled. Okay. So this is the fundamental thing of your adiabatic quantum computing, and on the basic part, I am moving towards the next portion. Oh, sorry. Yes. So we actually going for the optimization problem, mainly the constraints optimization. Maybe there are different kind of constraints optimization. One is maybe the coloring. You are doing the map coloring or graph coloring problems. You are a job shop scheduling problem, or any other. Maybe today's in a COVID pandemic, you are try to schedule the nurses in your hospital. So that also a some constraints optimization problem. Now let us move to the thing that what is the constraints optimization problem. You can see the entire landscape here. Some landscape is you can show, you can see that is a higher energy. If you can think that this is a this like a cloud and wave, and you can see that wave is up and downs, right? So on that you have a different rate points, and different rate points actually denotes the for a problem. These all different rate points are your solution set. So now that which rate point is a lowest energy level, you need to calculate. So you can do that way that you can sample this problem sets. So you sampled and you calculate that which one is the lowest energy level. You might be very difficult to find out really the which one with red dot is a lowest energy level. So classically, it is very difficult to find out that which solution is a optimized solution. So for that purpose, in a quantum computer, in an adiabatic quantum computer by quantum annealer, we will solve by these methods called binary quadratic model, that is called BQM. And a BQM is the class of problems that consist of basically Ising model and quadratic unconstrained binary optimization. The form is known as a QBO model. And BQM is basically taking as the quadratic part, and you can see that B summation of AI VI. VI is the constant for the ith elements and is a one qubit. Okay, you can say that QI, and here the another qubit QI to J. So I is influenced by J, and so Vi and Ji is the both the coefficients. For I and J is the sorry I and J is a coefficient, and Vi is a ith qubit, and Vj is the jth qubit. So this part is a quadratic part, and plus C is a some constant part. So this is one equation is a quadratic equation. Okay. So QBO model takes the following forms. So for each and every points, if you calculate, so you will get that AI is a one coefficient, Xi is a ith ith position values, and Bij coefficient and Xiji plus C, where this Xi and Gi are two variables or values, is the binary values is either 0 or 1. Okay. So corresponding Ising model is basically is denoted by just in place of Xi you are applied with a Hi is a coefficient, uh, Hi is a coefficient, and Si is a basically your spin, and spin can be considered as a -1 to +1. So 0 represented by a -1 and 1 represented as a +1, nothing else. So then this QBO model, you consider a variable Xi as a 0 and 1, and in that case you spin represented in case of Ising model. So these are the two model, one is a Ising and another is a QBO. Okay. So we will see how we'll formulate a problem in a Ising model or QBO model. We'll do that. Now then, what we should do? So we actually configuring the my objective functions with the qubit Qi, and definitely the coupler between that and this coupler is have a certain weight. So Qi and Qj, this is a quadratic part of your equation, as I told you. That's a Bij. Bij is a coupler weight, or you can say the strength. So objective is to that you need to minimize the values such that you get the objective to be solved. Okay. So next you can see one very interesting thing, that is a Q matrix. Actually what we do, we generate our cubo formulation, we for a given problem. Then we derive the Q matrix, and this Q matrix is simply sent to a quantum annular or a quantum adiabatic computing. As you can remember that Professor Panigrahi sir says that if you have a problem, you divide that problem into small piece, and this small piece of problem you convert into a quantum circuit, and this quantum circuit is run over a quantum processor, right? This is the gate level quantum computing approach. In a adiabatic or quantum uh, your annular, you develop a either QO or using formulation for a BQM, binary quadratic model, where from it you actually develop a Q matrix, and is a Q matrix you actually send to a quantum annular or quantum processor, quantum adiabatic computer. So Q matrix is a symmetric or upper triangular form. Either you can do the symmetric or upper triangular, means you actually do that for symmetric formations. So Qij and Qji all are symmetric. So Qij and Ji both are symmetric. So the value of Qij, if you can consider that this is your matrix, this is the I, this is the J, and this is the Qij. If you can see, this is the Qij position, and Ji is also sorry, it should be here, and Ji is another position, right? So suppose this is the Qij, and suppose this is a Ji. You understand this? Suppose I says 2 3. This is the 2 3. So uh, this is the position. Say suppose this is the position 1 3, and there is a 3 1, right? So these two are symmetric, right? So once these two are symmetric, if you are replacing to upper triangular, so you do the summation of these two, you do and divide by 2. So okay, so suppose this value is a 2, and this value is also 2, you do 2 plus 2 by 2. So ultimately it will reach to 2. And if you just making to upper triangular, just you can do the summation of these two to make it. So if you are making the symmetric, then you can do by plus Qij and Ji, uh, J comma I divide by 2, or by for upper triangular you can make Qij plus Ji. Uh, in every instance that will be required, and finally you get this type of matrix. You can see the lower triangular matrix all are replaced by 0. You can see that all lower. Any question? I will take some questions after this. So this is a lower triangular matrix. and you can see this is the diagonal. Oh, some noise is coming. Uh, you can see this is as A00, A11, A22, and so on, ANN. These all are diagonal elements, and 01, 0 to these all are off diagonal elements, right? So so if you can think that way, so you have a simply this, and you have 1 2 3, 1 2 3, and then maybe this one 3 4 5 6. So these are the off diagonals, and this is the diagonal part, and this is a lower triangular matrix. That's it. Now up to that, if any question I can take, because then I will go for formulating some problems to make understand about that type of what we have discussed. If up to that, any questions? uh, no question. Okay.
Yes, participant, any question? No,
i
sir.
think I think I will ask them, because so if the participants is already installed these things, then I must ask to install this to go for dwave setup. You can see that real your dwave login. I have already logged in my system. This is basically commercial and developer account, as I have actually US client, so they have provided me. But you can get a free access for 30 days if you just log in with your official mail ID. If you have official mail ID, you can go to just Google and type dwave login. Okay, you go to dwave login. Might be my network is slow. So you can go here. So dwave live login. So you can create your own ID. Actually, since I have logged in, automatically it will come. So you need to register. Okay, and what you need to do, you have a token here. You can see that in the left side you have a token. It will be expired, renewed, and automatically it will renewed because I have an annual package. API token, and you copy the API token by clicking the copy. Okay, once you copy, so you just go for dwave setup, or by applying the next info part, dwave config create. How you go for dwave config create? If you have already have a conda or anaconda, so you have an anaconda command line. You just use dwave config create. Okay, you just create the dwave config. So you have to configure your system actually. Let's wait, it will open. You can see that file already we have, because I have already configured my system and it is running, right? So then actually I asked to actually I have to place the yes. Why? So if I press a yes, so create a your profile new will be chosen. Why? So now your API, you can escape the API. So your authentication token, you can see my authentication token. So I just skipping that and the configuration step. So my token is actually showing. So here you can see that these are the same steps I just kept here. Okay. So that way you actually going to configure your system. Once you configure your system, if you have a system is configured, so what you can do to check that whether really your system is configured, you just do two things. You call dweb sample random. So it's a problem. It is actually now I'm just using the ping dweb ping. You can see what you can see. You can check. Firstly, I submitted a problem that is called ping. So I actually ping to the cloud dwebsystem.com, and then its API is a SPI, and from where I have actually ping DW 2000Q underscore 6. 2000Q means is a 2000 qubit processor, and solver faced in how many milliseconds, problem submitted and result faced, total CPU time, everything is given. So this is the part where you actually using that. I might be given a wrong statement. It's a random array in random problem. Yeah, it's not working. So you can check that the random problem is running. And obviously there's some error is happening. Why this is it error? Random sample. Yes, it's appearing some it accessed the hybrid binary quadratic model function 2. So hybrid quadratic binary model. What does mean by the hybrid quadratic binary model? I just want to show you the detail about that. What are the available solver or available processor you have. You can see there are hybrid server. Hybrid server means quantum and classical both are mixed. Okay, so always either we can use a hybrid or we can use a direct QPU, quantum processing unit. And you can see that now the quantum processing unit, one is called advantage, and this advantage is nothing else 5000 qubit, and DW 2000Q is a 2000 qubit, and these all others models. As you can see, the hybrid binary quadratic model version 2, so that model is actually accessed. You can see. Okay, so that is a part of how you can access the D-Wave. Then now, how you can use this D-Wave to solve the problem. This all are some things that I have written about all supported version. This is the all supported models. Not only it support binary quadratic models, Now it also support recently, very recently in 2000 November 2021, it is added with the discrete quadratic models, and obviously the constant quadratic models as well, and as well as penalty model. We will do some penalty model calculation today. And now this all of the samplers you are going to use, as I said, that hybrid solvers, the leap and classical solver is also there, is a simulated annealing, and quantum solver is a quantum, as you know, the 2000 Q and advantage. So these all are the samplers, the classical samplers, and your quantum samplers, and as well as hybrid samplers. Now let us move to some for one example. This example is that just is a very simple example. It need not to actually calculate, but I have taken a one very simple example first. Then I will go for a critical problem. So this is a V1 is a one variable and V2 is another variable, and you can see the BQM. What you want to do, that you need to check whether V1 and V2 is equal or not by a quantum computers. So what are the possible solutions that will give you that V1 and V2 are equal, and what are the possible solutions that are not equal? Basically, you are checking that V2 when the V1 V2 are 1. So cubo, then we are forming the cubo and using both we are forming here, and these are the solutions. These are the forms how you can actually design the cubo. So for instance, the x1 and x2, these two variables we have considered, and s1 s2 is a corresponding ising. When the both are 0 0, so definitely that is 0, because these are basically correct answer, right? So both are 0, so this is the v1 and v2 are equal, and when 0 1, then v1 v2 are not equal, so then you have given a penalty to 1. Now 1 0, so these are not equal, so you have given a penalty to 1, and 1 1, then both are 0, so the result is 0. So these are the values. Okay, so now how you actually moving to calculate the cubo formulation and Ising formulation? Now you can check the cubo formulation. This is the step 2, the make the cubo equation. As you know, these are the forms, and how these are actually calculated. How these are actually calculated. If you go for the step by step, each and every step, let us go for previous line. Oh. If I go for this line, so you can see you have x1, a1, x1 plus a2, x2 plus c equals to 0. So that as you can see that x1 is a 0, x2 is a 0, so a1 is automatically you can derive the value of a1. So c is a 0. From that you actually calculate the c is a 0. So from this equation you can understand this c is a 0, and obviously it is another value x1, a2, x2 plus x1 2, x1, x2 plus c. So this is the entire equation, right? So this is the entire equation of quadratic form of that problem. And as x1 is a 0, x2 is a 0, so these both are 0, so c is a 0. Fine. This c is a 0 you have calculated. Now for this combination, you can get x1 is this part is 0, but a2, x2 is a 1, so a2 come back. So here a2 is a from this equation, from this statement, you can calculate A2 is a 1, right? Allow again, from that you calculate A1 is a 1, right? So now you put for that A12. So A12 is a what? Is a -2. Is it correct? So equation convert x1 plus x2 minus 2 x1 x2. C is a 0, so it's a equals to 0. So this is a solution you can actually use. Okay, so you get back the every variables, every constants, and x1 x2 are the variables. It could be either 0 or 1. So you get your corresponding QO equations or QO formulations, quadratic binary model, and BQM, binary quadratic model, BQM. You have developed your sorry, just go back. Your equation QO Q1 plus x1 plus x2 minus 2 x1 x2. So this is your QO formulation, and similarly if you do for Ising, so it will be just a 0.5. Okay, that's different. Same problem, QO and Ising representations are different.
Dear participants, I think there is some internet issue from speaker's end. So we are trying to connect with the speaker. Please wait for some time and stay in the meeting.
Oh,
Yes, sir. Now
how
you are
long?
audible.
How long I was disconnected?
Sir, up to 3 minutes.
Okay, okay, okay. Thank God. One time it happened in my class. I was a 30 minutes disconnected. Anyway.
No issue.
So where I was explaining that the Q matrix which I have derived.
Yes, sir.
I have explaining the Q matrix which I have derived. That is, it is derived like this, and this is a 0 1 0 1. So this is a 0 0 position that I am saying that is I am saying that how the Q matrix is formed. The Q matrix is formed like 0 0 is a 1, 1 1 is a 1.
Sir, excuse me, sir. Please share
Uh,
your PPT.
Again I rejoin na. Okay, okay, yes. If I become in a full screen mode, then I can actually
Now
I want
visible,
no.
sir. Visible, sir.
Actually in a Gmeet it's a problem. If I in a full screen mode, I am nowhere in the world.
Okay, sir.
And
No problem. Then you can
now
continue with this.
no, one thing that no, I need to go. Anyway, in a full screen mode, otherwise it will not be visible to all things. Uh, now Now, one thing that I have is where I was in a discussion in which portion? The Q matrix I have defined. 0 0 is a 1. How 0 0 was a 1 is defined. So 0 0 is 1 defined. Then 1 1 is a 1 defined. Then 0 1 is a -4. Is it okay? So if I print this, now this Q matrix I have. Am I connected? Am I connected? Yes, I am connected, right? Okay. So this queue I actually sending to a real quantum computer, that is a quantum annealer, is in a form of BQM. And this BQM is you have using in a sampler by using one is by a classical sampler. Before that, if you are using the classical sampler, this one is a classical sampler, this one is a classical sampler, and this one is a quantum sampler. So I am showing now these two problems in a your quantum sampler and as well as classical sampler. One is the classical sampler. These two are extract solver is basically a classical sampler, and is this extract sampler I just running in the system. uh, is running. You can write this code in your own machine if you have already configured in between. I'm sharing this code with you for in your chat box, and participants you can run the same thing uh, or you now right now you can take a copy, and you further when you have ready your systems you can run this problem. Okay, in between I think this program is completed. Yes. So you can see, as I have already shows, that this is a -2. The classical sampler is showing the 0 1 1 is a solution when both the variables are 1. And 0 0 is another solution where the variable is a 0 basically. That is another solution, this because x1 x2 is the equal, and other these two are not a solution, but it's showing that energy is 1. So energy is 1 is a higher energy, so higher energy is not a lower lower Hamiltonian. So you are not calculating the lower Hamiltonian, but it's a classical solver. So that's why it's showing. But even in your real solver that I have for the time I have just already executed, you can see that where it is executed. It's executed in a quantum annular, and in a any question. Any question?
No, sir.
Okay. Uh, and in a quantum part, you can see that the it keep you sampling time. What is the sampling time you have used? You can just print by sample set information timing. Once you once you given this, so you actually get the all details of keep you time, the how it runs, and you can see now when you running in the QPU, you can see that 99 times, because you have given 999 times, because you have given 1000 samples. Okay, so 1000 samples, so that means 1000 times you are executing, and in 1000 times you are executing number of occurrence. 1 1 is a best solution when both two are equal, that is 99 times appears, and 0 1 is not a solution which is appears only once. So this is, you can see the percentage of giving the solution, the best solution is a 1 1, and that is done by your quantum annular or quantum adiabatic computing. I also giving this for your advancement or study. You can check when your system is ready. And last one, I have given just hash. Why I have given hash? I just simply ignored this statement. If I run this statement, it will take a couple of times. And what will expected to come? It will actually expected to come this figure. So just nothing else. It will take 4 to 5 minutes of time to coming from Canada. Jokes apart. So it's actually giving you the real scenario of solver details. So you have taken a two variables, so two qubits are there. So two qubits are, which is you have a coupler. So you can see the coupler is here, the Bij, and and this is x1 and x2, and this you can see the bias is given and solution you are getting. So both are one, and now this is your target QPU, and target QPU is I'm really told you that I have run in a 2000 qubit Pagusa. In a Pagusa architecture scenario, these qubits are interconnected, and in a Ising model you can see this is your qubits, and these qubits are connected. So for that showing, so you can use the inspector, so to show that your inspector, definitely dweb.inspector.show and sample set, so that will show you the actual real quantum processor and which number of qubits you are using for that problem, that will show. Okay, so now let us move to very interesting next part of discussion, that is the very interesting problem, that is a team creation problem, or you can think of that a graph coloring problem. As you know, the graph coloring problem is that is it an is it NP problem? Dear participants, are you there? Graph coloring problem. Nobody is replying. Okay. So it's a hard problem, right? So you can solve in a polynomial time. So now the same thing I have presented here for my discussion, that is uh, the just by using the team creation problem. The problem is that there are 8 participants are there, and we need to split in a group of peoples into 2 teams. How to pick the teams? And that must be same size, because 8 number of peoples are there. The 4 by 4 it will be there, and some of them are the friends. So there I consider the red and the blue. It will be three. That will be 2 groups, or the nodes will be colored. Now these are the graph that I have given for your problem. Okay, these are the graph I have given. So which one will be which color? That means that in a team. Okay. Now move to very quickly. Move very quickly that what those are friends. Those are friends to each others. Then you that should be in a same team, because if you and me are the friends, so it better we kept in the same team, so we will perform better. If I am you are enemy, so it better to go move to different team, otherwise team spirit will lost. So those are in the same team as those are friends, so that will be in the same team. So idea is that uh, what are the minimum number of cut you can make. So to make the team split, the number of parties split. Okay, so very large number of problems that can be denoted by same problem. That is maybe the graph splitting, uh, bisection, all these things. So here you can see the blue and red. You can see this blue and red are, though they are friend, but this connection represent the friend, but we are need to put that in a different team. So that is the minimum number. So what are the minimum number of cut you should do to get the better your team? So then you are going to solve it in a BQM by a quadratic problem, the binary quadratic model, QO model. And what the QO model I want to go, the objective minimize the number of friends that are split up. So by split up, we mean that they have an edge connected them that we are giving. So constants that rules, what is the constants here? There are constants in the 2 team must be a same number of size of people, right? So no team can be 5 or 3. No, that cannot be possible. So you can do that 4 only. Okay. Just a minute. Uh, so 2 team in the same size. So that is the constants. So what we'll do, I will denote the team 0 and team 1. And so suppose x1, x2, x3 are in the team 1, team 1, and another the team 0 is the x4, x4, x5. So that will be denoted by 0. So only that thing you get, that x result will you get, that all variables, that is a 8 variables, either it will be 0 or 1. So 0 means in this one team, 1 means in another team. Okay, so your result will be get that. Now, as I told you, the objective minimize the number of friends that are split up, definitely. So you have given a graph. Now this is, if it's a blue, then is good to be in the same team. But blue back, if it's a bad to be in a same team. So what is your truth table or objective? If it is a blue, then the good. If it is a blue-red, that is a bad. If it is a red-blue, that is a bad. And red-red, that is a good. So now do you represent in your form in that xi and ci? If it is a xi 00, that is a blue, is a good. Blue-red is a bad, the 01. So uh, blue-red, this is a blue-red, red-blue. Red-blue is a 10, so 0, bad. And red-red is a good. So now you represent in the corresponding values. So good is a 0 because a good is expected your solution to be, because both friend must be in the same team, so that is a 0. And bad is a given a penalty of 1, so bad is given a penalty of 1 and good is a 0. So you get your exact equations. So what you get the exact equations, as I told you that it's the xi uh, ai xi aj xj bij xi yj plus c, right? So now you can see that if you put the both the values of 0, so you get nothing else as c equals to 0. And in this way you solve it, c equals to 0, then aj equals to 1, ai equals to 1, bij equals to -2. So you solve it and you get the equation xi plus xj xi plus xj minus 2 xi xj. So that is the minimums. So you summation of that, so summation of all vertices, sorry, all edges coming from I to j. So you need to minimize these values for all pair of friends, right? So you have just taken the two pair of friends, but for the all pair of friends, you need to minimize that breaking. And second one is that constants is summation I, summation xi, so number of variables, summation xi it must be equals to 4 for all the participants. So 1 to 7 summation of xi is equals to 4. So that is the second constants model. So what is your constants? So that is this one. So if you draw, this is the your state line for x equals to 4. That will be the value. Now if you becomes the square, so it's if you do the square of it, so summation of that minus 4 whole square is nothing else a parabola, is a parabolic part. And its parabolic part, if you exclude this, and then it's a total cubo with this value is called a Lagrange, is a gamma is a, here is the one called a Lagrange constant. This Lagrange constant actually give you the some tuning towards the your quantum computer. So it is a programmer tune. Programmer need to optimize. The programmer needs to tune it and get the based optimized result. And this is a hunch also. So in your optimization problem, there is another value is called Lagrange, and Lagrange should be tuned such a way that to get the result to be constant optimized. So this is your finally the cubo, and that cubo need to be put in your program to get your exact solution. Okay, so I'm showing that. So this is the you are now going to give the lower upper triangular. One is the diagonal elements, and another is the off diagonal elements. So what is the diagonal and off diagonal? If you express this is very interesting. If you express this, so you will get xi square. Xi square means xi because is a xi is or either 0 or 1, so is a xi square is always xi, and plus 2xi zi, so is a form of ATAL. And then now is a 2 minus 2c xi, so this is the form of this. So c is here 4, so you get the minus 8xi, so minus 8xi. So if this is the xi square is I must say xi square nothing else xi. So 0 square equals to 0, 1 square equals to 1. So that is nothing else nothing else. This is you can see. Sorry, this you can see. So this is xi and this is 8 xi. So it's a minus 7 xi, and this is a minus 2 xi zi xi ci xi xa, and constant is 16. Okay, so what you are going to get, so that this is the this part is basically I'm sorry, this part is basically your diagonal part. So you can put the diagonal part from 0 to 0, 0 to 1, 0 to 7. So q is a q matrix, and q matrix ij, there's the ii position means 0 0 position, 1 1 position, this way. So all are you put the minus 7, right? And now for the j's, that is from starting from I plus 1 to 7. So this one the values, so which is the off diagonal values. You put a 2. Okay, now for off diagonal values, now you are including the another objective functions for that, which is your exactly the 4. So you have added this portion only. You can check that you have added this portion only. Okay, now your this portion. So this portion is xi1y, so definitely it will be plus. So you remove this one is a minus 6. This will be plus, so minus 6, and then this is a minus 6. So exact positions, and minus 2. So this is a minus 2, plus 2, and minus 2. So it's a 0 position. So this become your Q matrix, and that you need to send to your system. Okay, so what is your program now? I should write, I should show you, because might be my time will not permit. So very quickly I show you. uh, so that is the graph I have taken, as the same as I have taken, and in that graph I use the first constants. The first constants is, you can see the 7 into Lagrange. Lagrange I have considered the value. Lagrange, the gamma Lagrange I have considered as a 4, and you have given that for I to 1 to n. So it is about 7. So first one is 7 into Lagrange, and j I consider plus 2. Now this is for the constant part, and now this is for objective function for ij from every graph edge g. So for every graph edge g, if you there are g is there exist, if the edge exists in between I and j, so then I will use plus 1 plus 1. So I j j I put plus 1, and ij I will put minus 2. So for that case only, if there exists a edge, you can see, if there exists a edge, so you can see that the 0 to 4. So for 0 0 and 4 4, for 0 0 and 4 4, you have used minus 1 minus 1. So that is the plus 1 plus 1. And 0 and 5, if there exists a edge, so then you also use that thing. Okay, so that will continue for that part. And finally you use the sampler as a, you can see QPU true. That means your DOF sampler is a quantum computer, and you use that solutions, and you get this all 4 solutions. And all 4 solutions you can set the sample set, and you can only display the best sample set, and based on here I've display all sample sets. You can see this is your very interesting result, that uh, 0 1 2 and 4 will be in a one group, 3 5 6 7 will be in another team, another group or team, because it is the energy is a minus 62. And one thing that it is appears only once, as I have given number of count is only 10. So number of read is only 10 means I ask for 10 samples. And now one thing that, so that's why the number of occurrences, all number of occurrences is single, and a best solution is this one. And this is a chain. What is chain? The chain is a chain strength or chain break. If it is a chain break or chain strength, you have given a chain strength here. This actually is called as a embedding. How much your embedding is well. Maybe one qubit to another qubit, though those do not have any connectivity, so that embedding loses. So that's why you have placed a good embedding. So by including the chain embedding, so by applying the chain strength, if chain break is happened, so this value cannot be 0. If it is a chain break happen, so your value will be different. Okay, so that depends on the solution. As I explained, the value of alpha. You can see there are so many chain breaks. You can see there are so many chain breaks because of value of gamma. So if you change the value of gamma, so then you will get back uh, the chain strength. So here no gamma is given initially. So then chain strength is appears, chain break is appears. So you have put in the gamma, and for the gamma you have now again you can see some chain strength are there. So Lagrange value is a 4 is given. So now you can check whether there is a solution. 7.5, and now you need to tune accordingly to get that match of thing. So you can see that is the result, which is a 62, and number of occurrences is twice, and chain strength is 2. So only you can see in that example, there are two number of friends that are disconnected actually. So by just two disconnection age, you have a team. Two different team are developed by these two disconnections. Okay, so that is the, you can think of that as solution. Lagrange values definitely will be effective for your problem solving. Another part of things is a part of my research actually, which is already published by, you will be wondered about to know that the Sahil is undergraduate student, is doing this work with US company with different collaborators in US, is a epidemiology model and a COVID optimization. So this is a CIRD model. They have given with a transmission model, and is it a transmission and injection is given, and this is the, for instance, for India we have calculated, and what is the perfection of that? That is the lockdown. The optimization of lockdown is praised either by D-Wave or by classically, and we can see that the result of no lockdown and D-Wave plot. So if you have put the no lockdown, then what happened, and if you have put a lockdown, so in that nature is that. And now similarly you can see that if the lockdown is impressed, then what happened, with the availability of hospital during the COVID. And this is the another thing, that impact of GDP actually, how you are optimize the GDP, how you can balance between GDP and lockdown. Okay, so your classical NACSAP and quantum NACSAP is actually giving that the GDP, and you can see that quantum NACSAP is giving the solution, more better solution than the classical NACSAP. So that's all our result, and which is actually available in published material in web. Let us now move to few discussion about the NIQS. Just very quickly, I moving to NIQS because I don't have any very much more time. This is actually the quantum solution I am asking for. That is the Dodges and Josa algorithm. And this Josephson-Joshua algorithm is the finally the intention is that whether the function is a constant or balanced. If you have given a some number of variables x0 to xn, so if the function is 0 or 1, now the finding is that whether the Boolean function is a balanced function or a constant function. So for the classical solution, it will be actually required the 2 to the power n number of computing because of there are n number of variables. So you can put either 0 or 1, and then the constant function will be returned all zeros or all ones for any inputs. Mm. If you have a two x1 x2s, and balance functions is return zeros for exactly half of inputs and ones for exactly half of other inputs. Excuse me, there should be only 1 0. All are become zero zeros. No, it's 1 zeros. Uh, Now actual circuitry is that, so you actually do the Hadamard transformation, the parallel Hadamard transformation over all inputs of your functions, and there are one input function, this is called 1, so checking that whether balance or not, and you have made one your quantum oracle, and in quantum oracle you have expressed that x and y zor of function of fx. So function of fx is a function which you actually testing for that whether it is your constant or not a balanced function. So again, then you step three, you do step two, you step three, you do the again Hadamard transformation of upper n bits, and from the upper n bits you read the data, and if you found all the zeros or all the ones, so then it's uh, constant functions, or if it is half of the input is a 0 and half of the input is a 1, so then is a balance function. So that is actually implemented by different in these steps, uh, and this will be finally you measure the lower half of the inputs, and we'll check that whether evaluated that one fx is a constant, if 0 fx is a balance. So that is the measurement part you will perform with this mathematics. Now, actually, how you actually do this thing, I just want to show you. If time permits, 2 minutes I have. So already I have run it. This is your function actually your fx functions. You can check that you have applied Hadamard transformation, and in Hadamard transformation you have applied this one. You have Hadamard transformation, then Hadamard transformation you are applying the function. The function is given. So this is the function, and then again the inverse Hadamard transformation, and from the top of the first n bits you actually uh, you actually calculate the whether the result is your constant or a balance. Okay, so due to lack of time I am not able to explain it properly, but if you want I can share this all my uh, contents which I have prepared for this work FDP. I will share to organizers that they such that my participants will be benefited for that. Now any questions? uh,
Dear participant, if you have any question, please unmute yourself and ask the question. Any question? You can
might
unmute
be
yourself and ask.
might be there not in right time to ask any questions, uh, because they need to they need to work hard. So for that purpose, I giving my mail ID to all of you. If you have any question or any further in your research career or any discussion, you can call me. Just put a mail. I'll be happy to share everything or collaborate with all. Thank you.
Thank you so much, sir. Thank you so much for enlightening us by your valuable knowledge and for your valuable time. You have covered so many topics like NIQS, qubits, quantum annealing, constraint optimization, then quantum annealing programming model, Q matrix, then D-Wave configuration, and the most important thing is you are given the hands-on knowledge. I hope that each and every participant will get benefit of the knowledge that you have shared with us. And even though you are facing so many problems, you have managed to conduct the session. I thanks on behalf of Computer Engineering Department, MIT Institute of Engineering, Bhujbal Knowledge City, and on behalf of all the participants, I thank you I thanks very much, sir.
Thank you. Thank you very much. All about to my our to God that I am now okay, and I successfully delivered my lecture. Actually, just just 5 days before, I was not in a position to talk. That time I was very critically facing throat problems as I am infected by COVID on a Jan 1st January 2020, 2022. So
Yes, sir. And,
only
the
five
most
days.
important thing you have taken it hands on. So I think the passion which force us to anyhow conduct the session, passion
Yeah,
towards something.
yeah. I wish that all participants go through that all things I have given, and I will share my entire things to entire folder to organizers. They will share with our participants, and they if they try to do that, they will be able to know the what a quantum annular is. And from IBM Q, I have given one Dodge's algorithm, Dodge's algorithm. That is a balancing algorithm. So very simple algorithm. So you practice all. If you have practiced, so you automatically it will be understand how to calculate the next one. So I have given another one problem solving in a Cubo, one tutorial for that. So they will able to calculate their own different problems cubos, so that they can run in any quantum computer. And everyone, please enjoy your free license in D-Web for 1 month. They are usually giving by using your Gmail. Even if you have a Gmail account, so that they are that also accessible. So all people's all participants can use the D-Web because of D-Web we have a 5,000 qubits. You can run really your very large data sets in that application. Even as we are doing the real life programs, actually nowadays we are doing the your financial portfolio management for one US company, as I told you. So we are doing that part of that financial portfolio management part. They're actually they are preparing from us for research part, and they will sell it. So that is a part they are using commercially. Hmm. So thank you very much giving this opportunity to discuss with all of you. As because all the bright newcomers in a quantum computer domain, we need a very good ecosystems. Don't be hesitate to discuss if you have any interest or any thing you want to know. Please come. We should build a big ecosystem, because that's why the AICT and central government is trying to deliver this type of FDPs. They're funding for these FDPs, and even to me, I have also several quantum computing projects funded by central governments. For only the focus is that we should develop our own ecosystems in India. Okay, so all our community, I am requesting in this platform, make a community of quantum computer with this Institute of Engineering, Nasik. It will be very worthy to be there. I want to be a participant in that part, as a maybe you in that forum. You definitely you have a one WhatsApp group for this FDP. So then you convert this into a forum where the quantum urge or quantum interest will be flowed in the next stage of learning. So we definitely can do uh, a miracle. I must say a miracle. Okay, that's thank you,
Sir,
thank you.
excuse me, sir. We have received one question from the participant.
Yeah,
So
yeah,
they are asking how many folds D-Wave gives performance than GPU.
yeah. One thing that uh, if you are talking about the only the part of that, the GPU is a part of the hybrid. If the if you don't use the only the using the CPU, then you go for the GPU actually. That is the part of GPU and hybrid computing. But once you go for the KPU, that you can get that optimized result of optimization. The result is optimized as just I showed you. When you are running in a classical, then you may be giving the all four possible solutions. Those are not optimal solutions. But quantum quantum annealer on KPU is giving you the more towards optimized solutions in terms of your lower level of energy in a Hamiltonian. Okay.
Any other question? Okay, thank you so
At
much,
least,
sir.
at least few of participants have interest to that.
Yes.
Otherwise, they definitely they gradually they will have different questions in mind. Thank you.
Thank you so much, sir, for your time. And I hope that all the participants will get inspired by your words and your valuable knowledge that shared by you. Thank you so much, sir.
Thank you. Thank you.
नेक्स्ट सेशन के साथ है ना सर?
Dear participants, the next session will start at 2:30. So please join on time.